So hello everybody, good morning, welcome to lecture 29. So in the previous lectures, we've been talking about the Biot-Savart law. First of all, am I audible? Can you please confirm?
Yes, sir.
Yes.
Okay. In that case, you might have heard me ask some of you to turn your videos on, so I would be grateful if you could do that. And please don't make me ask again and again. Thank you. Okay. So we have this Biot-Savart law, and we have Biot-Savart law, we have Ampere's law, and we have the Lorentz force law. So these are all associated with okay. So these are all describe the behavior of magnetic field and the forces due to magnetic fields on moving charges and on currents. And so the first law tells us that what is the magnetic field generated by steady current. This law tells us what is the force on a moving charge due to a magnetic field. And this law is another statement of the Biot-Savart law. Okay. Now, so in the last, so it might seem like we have a whole bunch of different laws for magnetic fields, but that is not really the case. These are all different aspects of the same description. Describing that framework requires a little bit more mathematics than we can talk about at this stage. But I want to assure you that one of the nice things about physics is that there's a certain unity of ideas and subjects, right? So that is maintained, that continues to be maintained. So we don't have like chemistry or biology or some of the other sciences where we don't have such a full complete understanding yet. You know, you have to learn many things. You have to learn about the nervous system separately. You have to learn about the digestive system separately, and so on and so forth. When of course they're all part of the whole, you know, same organic whole, but we don't have a proper theory to describe everything the same way we do in physics. So all of these are actually aspects of the same law, which are known as Maxwell's equations. Now, so in the previous class, what we did was we used the Lorentz force law, and we use that to describe the force on a steady state current due to a magnetic field, right? And so that force is relatively simple to write down. If you have a straight wire and you have a constant magnetic field. So in that case, the force on the wires becomes this expression, B cross L, vector L, where L is the length of the wire and the vector gives you the direction in which the current is flowing. If your wire is broken up into segments, so if you have a wire which is like a square, for instance, in this case, right? So what you can do is you can just apply this equation to each side separately, right? Alternatively, what you can, and if your wire is not, made up of straight pieces, if it's like a circle or something like that, then you have to work with this equation. You have to integrate this equation because this dl at each point keeps changing. Right? So since dl is not a constant for any section of the wire, you have to do that integration. Okay, so today what I will do is I will work out the force of between two wires. Okay. So for this purpose, what we need is, first of all, well, we need two wires. Okay. And we'll take the case where the wires are initially perpendicular to each other. Of course, you can have other configurations as well. And let's say the distance between the two wires is capital R. And the first wire is carrying some current I1, and the second wire is carrying some current I2. And again, the assumption in all of this is that these currents are steady. Okay. Steady state currents. So this is an important assumption. Okay. Now, in previous lecture, so when we talked about the Biot-Savart law and also the Ampere's law, we had worked out the magnetic field due to a current carrying wire, right? And that magnetic field comes out to be this not equal, B is equal to mu naught I by 2 pi R, right? So I can use the right hand rule to determine the direction of this magnetic field. The magnetic field will be pointing perpendicular to this radial vector. This is the radial vector. Then the magnetic field here is perpendicular to this vector, and it's also perpendicular to the current I1, right? And what is the magnitude of this magnetic field? Let me call it B1. It's the magnetic field generated by the first current. So B1 is equal to mu naught I1 by 2 pi R, right? But in exactly the same way, what will happen is that I2 will also generate a magnetic field, right? And that will have a magnitude mu naught I2 by 2 pi R, right? So you can use either one of these, okay? It doesn't matter which one you use, right? And since both of these wires are infinite wires, we don't need to do any complicated integration. All we need to do is we just take some segment of this wire, right? And we know that the magnetic field is pointing in the perpendicular direction. We know that the current is flowing in this direction, right? And what is the, and this direction is the dl vector, right? So I can use this expression to calculate the force on the second wire due to the electric field of the first wire, right? So F is equal to I2 times dl cross B, right? Or I can write df if you like, that's better. Now dl and B are perpendicular to each other, right? You can see that from this picture. And so this just becomes IT, and this will be B1, right? B1 dl, okay? And the direction, let's say this direction is the Z direction. So then what will be the direction of this vector? L is going up, B is going in this direction. So L is up, B is in this direction. So the force will be in the direction of my index finger, right? L cross B, right? Yeah, L cross B, like L cross B. So the force will be pointing in this direction. I'll call that F12. The force on the second wire due to the first wire, dF12. And this is the Z axis, and we have, let's call this the X axis and the Y. So if you want to be, if you want to write down the direction of F12, F12 is in the direction of the minus Y hat direction, right? Now, what is the total force? The total force would be the sum of all the forces on the whole segment, right? But this, if you look at this, you'll get B1 I2 Y hat integral dl. But integral dl is equal to infinity, right? Because the length of the wire is infinite. So instead, what we can do is we have on this side, we have df, right? So we'll write df12, and we'll just look at the magnitude of df12 divided by dl. So that's force per unit length of wire, right? And what is this df12? Again, just the magnitude. It's equal to B1 I2. So what is this? Mu naught I1 I2 by 2 pi r. Right? And this force is attractive. You can repeat exactly the same calculation with dF21. dF21 will be I1 dl cross B2, and you will get minus I1 B2 dl, plus y hat. Now this force will be pointing in the positive y direction, right? And df. So you will get exactly the same answer. D of F21 by dl is equal to mu naught B2 I1, and B2 will be exactly the same, right? So this is the force per unit length between two parallel wires. And if the wires are anti-parallel, if the current in the wires is running in opposite directions, so I1 in I2, then the forces are going to be repulsive. Again, we'll have to write down the force per unit length. So dF12 by dL you'll get exactly the same answer, only the direction of the forces will be different. Any questions? Okay, then. No questions, huh? Okay. All right, then I will start talking about well, I've already talked in some detail about Stokes' theorem. I'll just remind you what the expression for Stokes' theorem is, okay? And then we'll look at a couple of problems related to Stokes' theorem. Okay. So Stokes' theorem is a statement that if I have some vector field B, so let me write this down, then I will make it more precise. The statement of Stokes' theorem is, well, this equation. And what is the interpretation of this equation? Again, let me go back to one of my previous slides. So I have explained Stokes' theorem in some detail, right, in lecture 24. So in case you have forgotten all of this, you can go back and consult that lecture. All right. So what this theorem says is that I have some surface and it is an open surface. That means it has a surface. It is a surface with a boundary. Or a hole, right? It can also be holes, more than one hole, right? So this is our surface. It's like a section of some ball or a cap or something, right? It looks like a cap. And I have a magnetic field, some vector field, which is defined everywhere. And what I do is I take the curl of this vector field at each point, okay? So let's say that the curl of this vector field turns out to be, the curl of a vector gives me what? It gives me another vector, right? So I have the curl of the vector field at each point. Then I have the area vector dA. So I calculate the flux of this vector field. Okay, so I have one vector field B. I take the curl of this vector field. I get a third vector field B. Right now, given any vector field, I can calculate the flux of this vector field through any surface, right? The flux of V through the surface S, right? So this is my surface S. But the main thing is that this surface is open, so I should not put this circle, right? It's not a closed loop. It's not like a closed loop or a closed surface, right? That's when we put this circle. So I calculate the flux of this vector through the surface, right? And then the statement is that this flux can also be evaluated by going around this boundary. Now, this is an open surface. It has a boundary. So what do I do then? I take this vector field B and I take the line integral of B around the boundary. Okay. Okay. Now, as I was telling you earlier, all three of these laws are aspects of the same same force, right? So we can actually see how that happens. So we can start from the Biot-Savart law, for instance. The Biot-Savart law looks like this. I times dl so this is the magnetic field at some point R dl. So again, let me remind you what the geometry looks like. You have some segment just carrying some current di. You have some point R. Okay, so you have some coordinates. In those coordinates, this point is a fixed point, it's R. And this wire is at some location, R prime. And so this vector is R minus R prime. So the magnetic field at R, that means the magnetic field at this point, due to the wire, is equal to dl cross this vector, the direction vector, divided by this vector cubed. Okay. And then you integrate over the length of the wire. So wherever the wire is, you do that integral. As you do that integral, what will happen? R, this vector R will be fixed, right? This is the fixed point. We're calculating the vector field at this point due to all the points along the wire. But this vector R prime will keep changing, right? Because let's say you have a wire like this, right? I have to break this wire up into segments like this, right? And I have some point where I want to calculate the magnetic field over here. And let's say this vector is R without a prime. right? So what do? I take my wire, this is my wire, right? I break it up into small pieces. Each piece lies at some coordinate. So these are my coordinate axes. Each piece lies at some location r prime. And then this vector is r minus r prime. Take this, move it down here. Right? So I find the magnetic field at this point due to this wire, due to this segment, right? And then I move along the wire. That's what this integral is. I'm moving along the wire and summing up the contribution from each point of the wire. As I move along the wire, what happens? This dl vector keeps changing, right? Because dl gives me this tangent vector. And r prime is the location of this segment, right? So r prime also keeps changing. Okay. Now, so I'm not going to work through the details of the next I'm not going to go into the steps in detail, but the final result is the following. And if you are really interested in the steps, you can look at it in section 5.3.2 of Griffiths for the full derivation. Okay. What happens is that, so I have this magnetic field. I can do different things with a magnetic field. This is a vector, right? I can take the divergence of vector. I can take the curl of the vector. So if I take the curl of the vector, what happens is I get a very simple result over here. Okay. So the curl of the vector becomes mu naught times j. So let me now explain what this meaning of j is. What is this j? Okay. So this vector j is what we call the current density. Okay. What is the meaning of the current density? Well, let's say that you have some wire which is carrying some current I. Okay. And imagine that you have a wire which has a greater radius, a greater cross-sectional area, right? So this is A, and this cross-sectional area is A prime. And now let's say that this wire also is carrying the same amount of current. Okay. What that means is that if I look at any cross-sectional area and I ask how much is the charge passing through that surface. So I ask how many electrons are moving through this surface or through this surface, right? dq by dt. Here it's equal to I, and here also it's equal to I. Right? But clearly you can see that here these electrons have more area, they have a larger space in which they can move, right? And here they have a smaller space. Now let's assume that the number density of electrons or the number density of charge carriers, right? Let's say that the number density in both wires is the same. So if the number of electrons in any small region is the same, how can I get the same dq by dt for this small area as for this large area? How is that possible? Anybody? So you can think of this in the following way, right? Instead of electrons and wires, you think of water flowing in a pipe. Right? So I have water flowing in a pipe. Again, I have two pipes. Okay. Some water is flowing in the two pipes with some velocity v in this case and some velocity v prime in this case. Now, the total amount of water that is going through each pipe is the same. So if I look at instead of v, I'll use u because that will look vector u prime. And dv by dt is the rate volume rate of flow of water, right? So the volume rate of flow of water in both regions is the same, let's say, okay? Then what can you say about u and u prime?
U prime is more than U.
U prime is less than U.
Right. Right? This also follows from something known as Bernoulli's theorem in hydrodynamics. Right? This equation also comes from Bernoulli's theorem, right? Now, if for those of you who are familiar with it. So here what you have now is the same thing. You have the number density of, and the water is an incompressible fluid, right? So the number density of water molecules does not change. If water was not an incompressible fluid, incompressible means you cannot compress it, right? To squeeze the same amount of water in a smaller volume. If water was a compressible fluid, what would happen? You could take the same amount of water that is flowing in this region. So these are all water molecules now. And you could squeeze them into a smaller volume. And in that case, these velocities could be the same. But water is incompressible, right? This is an important assumption. Here also, these electrons, this electron gas, right? These electrons or whatever the charge carriers are, these also form an incompressible gas or incompressible fluid. Can you tell me about this situation? The current I is the same in both. What will be different is that the velocity of charge carrier than V prime, right? A greater drift velocity, right? But the behavior is not exactly the same, right? So if I keep making this wire bigger and bigger, what will happen? The drift velocity will become very, very small, right? So how do I describe, how should I describe the flow in this case? How should I describe the flow in a way that doesn't depend on the shape of the wire? How to describe flow in some way that is independent of the wire's cross-sectional shape, right? So it should not matter like what this area is or what its shape is. And the answer is that you have to use this quantity, which is called the current density. And we write it as di by dA. It is the rate of flow of current per unit area. Okay, and it's actually a vector. So I should write it like this. Vector di by dA. This is the current density. Okay. So what does this mean? This means that, let's say again, you have some surface, okay? Now, if the current flowing through this surface is in this direction, okay? I, right? Then, and let's say this is the x-axis. So this is equal to I times x hat. Then what is the current density through this wire? The current density is going to be just be equal to I by A x hat, right? I is a uniform quantity. It's the same for all the points, okay? Okay, 1 second. Okay. But you can also have a situation where, for example, the current density in a wire is not uniform. As an example, you can think of something like this. Let's say that, again, this is the x-axis. Some current is flowing in this direction, but the current density is not uniform. So let's say that my current density is equal to some J naught, okay, times R square or times R by. So it's a function of the radius R, okay? It's a function of R. So that means when I go to a certain radius over here, and I look at a very thin, concentric shell, a thin cylinder, which has some radius R. Amaya, the speed of the charge carriers, if it's not different, then how will you have the same current flowing in the two wires with the same charge density? Look, I'm just giving you an illustrative example, okay? I'm not saying that this is exactly how electrons behave in metal. All right, I'm not teaching you the theory of conduction. I am giving you an example. I'm saying that the electrons are, and Amaya and everybody else, it is please much better if you can ask your questions rather than typing them in the chat, because for anybody who watches this on YouTube, they don't know what the question being asked is, right? They only hear the answer. So the question is, how can the speed of charge carriers be different? Electrons have the same speed. So as I said, I'm not talking about the properties of real conductors. I'm just giving you an illustrative example to talk about charge density, current density. You have two wires. In it, there are some charge carriers. Those charge carriers have the same concentration, the same density per unit volume. And both the wires are carrying the same amount of current. So if they're carrying the same amount of current, then the charge carriers in this wire have to move at a faster speed. It's simple, that's it. There's nothing more complicated to it. You just have to fit more items per second because there is less space to go in this region than in this region. That's it. The speed of electrons is not the same, by the way. The speed of electrons, which is the drift velocity, it depends on the current. So if you look at Ohm's law says that the drift velocity, you can calculate the drift velocity, it depends on your current, okay? Now, so let's say I have some a wire like this, which has the current density is a function of the radius, okay? Now I can ask, what is the total current in the wire? So the total current in the wire will be
J dot dA.
J dot dA integrated from R is equal to 0 to whatever is the full radius. Let's say the full radius is capital R. Okay. And what is dA going to be? dA is, you can take the volume of this surface area of this shell
2
over
pi
here.
r dot dr.
2 pi r dr. I'm sorry, Sukreta. I know that maybe for some people I'm going too slowly. And so this becomes r by r. When I take the dot product, I just get 1, 2 pi r dr. Right? So this becomes j naught 2 pi j naught by r integral r square dr, which gives me 2 pi j naught r cubed by 3r, which is equal to 2 by 3 pi j naught r square. So this is the total current flowing in this wire, right? And again, you should always check the units. Here I've said this is the current density. So current density has units of, what are the units? Current per unit area. So the units of current is coulombs per second. So it is coulombs per meter square per second, right? So here I'm calling this the current density, and here I have J naught times R by R. Now this is dimensionless. So this has dimensions of current density, coulombs per meter square per second. And in my final answer, I get that I is equal to this expression. Now I have J naught, which has current, this, and I get something with units of current. Okay. So this is the density. You can see current density, sorry. And if we use the current density, we don't need to worry about, the cross section. So I think of it in this way. I is an extensive quantity. Okay. I is an extensive quantity, like the total volume or total number of something, of or a fluid material, it doesn't matter. But J extensive and intensive are, I'll just mention those in 1 second. Like the number density, pressure, temperature is also an intensive quantity, right? Or mass density. These are all intensive quantities. What is an intensive quantity and extensive quantity? If you have if I have 2 wires, right? Let's say I have 1 wire here and I have another wire here. And this wire is carrying some current I and this wire is carrying some current I. Then what is the total current in the 2 wires? It's I, let's say I1 plus I2, right? So an extensive quantity is something that depends on the size of the system. As your system gets bigger or smaller, the quantity changes. So if you have the total volume of some gas, it's an extensive quantity. The total number of particles is an extensive quantity. On the other hand, if you look at the current density, so again, I have 2 particles. I have 2 wires which are carrying some current, okay? And let's say that the first wire has some current density J, and the second wire has the same current density J. Okay, just for assumption's sake. So this wire might have a different cross-sectional area. So let me make it like that. This wire might have a different cross-sectional area. And so this current will be less. Sorry, the current will be greater. This current will be greater than this current, so that both the wires have the same current density. Now, what is the current density of the whole thing? The average, on average, of the two wires combined, it will still be J, right? Okay, so this will be I1, A1 and A2. So in the first case, you have J is equal to I1 by A. In the second case, you have J is equal to I2 by A, right? So what is the current density when you combine both the wires? I1 plus I2 over A1 plus A2. Now you can write this as A1 times J plus A2 times J over A1 plus A2, right? And this just becomes equal to J. So this current density is an intensive quantity, like the pressure, right? So if I have some volume of gas, if I double the volume, if I look at this, what happens? The total number of particles changes, the total volume changes, but the number density doesn't change, the pressure doesn't change, the temperature doesn't change, and the mass density doesn't change, right? So now, just to remind you that Gauss's law can be written in two ways. The first way is an integral, and you can think of this as the extensive version. And the second is a differential, which we get by using the divergence theorem. And this is the, you can call it the intensive version of the Gauss law. And what is the quantity here? It's the charge density, right? And same thing we have for magnetic field, right? Only thing is with the magnetic charges density is 0. So for currents, what do we have? We have two laws. One says that B dot dl is equal to mu naught I enclosed. Now this is the total current. So this is an extensive version. Then the other version is the following, that curl of B is equal to mu naught J. This is the intensive version of Ampere's law. So how do I relate these two? I relate these two using Stokes' theorem. So I have some surface. I take the curl of B, integrate it over that surface. Again, it's not a closed surface, so let me write like this. What is this? This is integral over the surface of mu naught J dot dA, right? Now,
Yes.
what is the integral of, Sorry?
Nothing, sir. Continue, sir.
So this, what is the integral of J dot dA? That is just going to give me the total current through the whole surface, right? This is the first thing. On the other hand, I know from Stokes' theorem that this expression can be written as integral B dot dl. So these two are equal to each other. So B dot dl is equal to mu naught I enclosed. And this is actually there's a circle here because the boundary is closed, right? Let me try to show you some illustrations of this. If I can find some. Okay, can I take say 10 more minutes or maybe less? Would that be okay?
Yes, sir.
All right. So let me just show you some animations. Okay. Let's see. Okay, so we'll continue with this. Can I start the screen sharing? Share sound. Okay.
Or maybe they represent the force of gravity at many different points in space, or maybe a magnetic.
So is the sound from the video audible?
Yes, sir.
Okay. So this is that same video we had looked at
Field strength.
a long time back.
Quick note: the flow is slow at
And
the
we had talked about divergence and all.
south end of a magnet in isolation
And curl.
don't exist. There's nothing analogous to positive and negative charges in an electric field. Likewise, the last two equations tell us that the way that one of these fields changes depends on the curl of the other field. And really, this is a purely three-dimensional idea, and a little outside of our main focus here. But the point is that divergence and curl arise in contexts that are unrelated to flow. And side note, the back and forth from these last two equations is what gives rise to light waves. And quite often, these ideas are useful in contexts which don't even seem spatial in nature at first. To take a classic example that students of differential equations often study, let's say that you wanted to track the population sizes of two different species, where maybe one of them is a predator of another. The state of this system at a given time, meaning the two population sizes, could be thought of as a point in two-dimensional space, what you would call the phase space of this system. For a given pair of population sizes, these populations may be inclined to change based on things like how reproductive are the two species, or just how much does one of them enjoy eating the other one. These rates of change would typically be written analytically as a set of differential equations. It's okay if you don't understand these particular equations. I'm just throwing them up for those of you who are curious, and because replacing variables with pictures makes me laugh a little bit. But the relevance here
Yeah, don't worry about these equations, okay? Just try to look at the...
is that a nice way to visualize what such a set of equations is really saying is to associate each point on the plane, each pair of population sizes, with a vector, indicating the rates of change for both variables.
Right, so what you have is, you have some system, okay, which you're talking about a population of rabbits and foxes. And rabbits eat foxes, right? Sorry, foxes eat rabbits. Foxes eat rabbits, right? But rabbits also tend to multiply very rapidly. So now you can set up an equation which describes the rate of change of rabbits and foxes, right? That is this equation over here. But you don't need to worry about the details of this equation. What he's showing you, what he's telling you is just how this vector field shows up. So you have this x-axis and y-axis, and there's a rabbit population and there's a fox population. So you can see that at some point there are, let's say, 20 rabbits and 40 foxes. So you would write that as a single point over here, this white disk. And then after some point, let's say the rabbit population and the fox population, but they both decrease, right? Because the foxes eat the rabbits, and so the rabbits become fewer. But then because the rabbits become less, the foxes also go hungry and they die. So the foxes also decrease. So what happens is that there is a change in your rabbit and fox population. That rabbit and fox population, that change can be represented by a vector. Right? So he's just showing you this as an illustration of a vector field.
For example, when there are lots of foxes but relatively few rabbits, the number of foxes might tend to go down because of the constrained food supply, and the number of rabbits might also tend to go down because they're getting eaten by all of the foxes, potentially at a rate that's faster than they can reproduce. So a given vector here is telling you how, and how quickly, a given pair of population sizes tends to change. Notice, this is a case where the vector field is not about physical space, but instead it's a representation of a certain dynamic system that has two variables and how that system evolves over time.
So just to emphasize again, this is not a vector field in like real space, okay? This is a mathematical representation, but it's still a vector field, okay?
This can maybe also give a sense for why mathematicians care about studying the geometry of higher dimensions. What if our system was tracking more than just 2 or 3 numbers? Now the flow associated with this field is called the phase flow for our differential equation, and it's a way to conceptualize, at a glance, how many possible starting states would evolve over time. Operations like divergence and curl can help to inform you about the system. Do the population sizes tend to converge towards a particular pair of numbers, or are there some values that they diverge away from? Are there cyclic patterns? And are those cycles stable or unstable? To be perfectly honest with you, for something like this, you'd often want to bring in related tools beyond just divergence and curl. Those would give you the full story. But the frame of mind that practice with these two ideas brings you carries over well to studying setups like this with similar pieces of mathematical machinery. Now, if you really want to get a handle on these ideas, you'd want to learn how to compute them and to practice those computations. And I'll leave some links to where you can learn about this and practice if you want. Again, I did some videos and articles and worked examples for Khan Academy on this topic during my time there, so too much detail here will start to feel redundant for me. But there is one thing worth bringing up regarding the notation associated with these computations. Commonly, the divergence is written as a dot product between this upside-down triangle thing and your vector field function, and the curl is written as a similar cross product. Sometimes students connection between divergence and the dot product, and between curl and the cross. Imagine taking some small difference to your function over small steps is what differential calculus is all about. Now, the dot product of this step vector difference vector cross product, if a feels like it's just about you and
so maybe
me sharing in a love of math with no other motive, especially in the cases where the viewers are students. There are some other reasons, and I wrote up some of my full thoughts.
Anything useful? No, I can't really find anything useful. Never mind. Okay, so I guess I'll stop this. All right, so yeah, that we don't, I guess there is no really useful animation or visualization of this. Let me try something else. Just trying to find some decent imagery. I can't seem to find it. Okay, so I will leave you with this. Which is Khan Academy only. And interestingly, Khan Academy is also available in different languages, well, at least in Hindi. So if that is useful for any of you. And as it says, this article is for physical intuition, okay? The physical intuition means for understanding the concepts in a physical manner, okay? So it describes what the Stokes theorem is and how to understand the line integral in 3 dimensions, okay? So this is the animation, I guess, that I'm looking for. So this is some 3-dimensional vector field. And in this 3-dimensional vector field, you take a closed loop, right? So you have some vector field and you have some closed loop in this vector field, okay? Which is shown with this red. Then at each point along the loop, you pick an orientation. So this is gives you the orientation, right? So this, they gave a nice thing. Imagine you're a bird flying through space along the curve C while the wind blows according to the vector field F. So this ball, this white ball is the bird, right? So what will happen is there will be some force which acts on you, and that force will be given by this F dot dr, right? Now, what is F dot dr? When you take F dot dr along the closed loop, you will get the work done when the bird goes along the closed loop, right? So if F has some rotation, what will happen? The bird will have an easier time flying around the loop, right? But if the field is perpendicular to the direction of the loop, the bird will have a very difficult time. So that's what this line integral does. It measures the tendency of the fluid flow to circulate around C, okay? And similarly, the rest of this article shows you how to calculate the curl on each piece of the boundary, okay? So I'll leave you with this. I'll share this in the chat and the Telegram, and then we can stop over here. And I will stop the recording and